Hello everyone, this is Ala Tejavardhan, EC department from RMD Engineering College. Let's look into our mini project Transmission Line Characteristics in Transmission Lines and RF Systems. My project guide is Mr. Bharti Dasan sir, Assistant Professor, EC department from RMD Engineering College. Let's look into it. Let's look into our project. So our objective is to calculate the characteristic impedance and propagation speed of a transmission line. So this is an infinite transmission line, what we are seeing here. So what is a transmission line? So from the power generating station, the power goes to the substation, and from the power station substation, depending upon the user's requirement, using the step up and step down transformers, it is transmitted through the transmission line. The transmission line may be a 2-wide or coaxial cable, or it may be anything. So this is an infinite line. So any pair of conductors separated by an insulating medium creates a capacitance between those conductors. So this is how the capacitors are formed in this infinite transmission line. Now what happens when the switch closes, voltage applied between two conductors creates an electric field between those conductors. Energy is stored. This is the first conductor and this is the second conductor. So between this, the energy is stored in the electric field what is generated, and the storage of energy results in the opposition to the change in voltage. The reaction of a capacitance against changes in voltage is described by the equation I equal to C into dE by dt. So we have come across this equation so many times, but this is how the equation actually came. By this situation, so whenever there is a electric field between those conductors, the energy is stored in this electric field, and the storage of energy results in opposition to change in the voltage. So the voltage is described by the equation, the change in voltage I equal to C into dE by dt. So we know that how the so therefore the electric field produces here. However, the current drawn by a pair of parallel wires will not be infinite because there exists a series of impedance along the wires due to inductance. So these are the inductance formed in this infinite transmission. Also we know that the current through any conductor develops a magnetic field. Each wire develops a magnetic field as it carries charging current for the capacitance between wires, and therefore the drops in voltage is given as E equals to L into dI by dt. So this is how again this equation comes, which we have come across so many times. Due to electric charge carriers in the wires transfer motion to each other from each other nearly at the speed of the light. So what happens, this is an uncharged transmission line, right? So what happens when we switch on the transmission line? So it nearly the electric charge carriers in the two wires transfer motion to and from each other at nearly the speed of light, that is 3 into 10 to the power of 8 meter per second. So the wavefront of voltage and current change will propagate down to the length of the wires, and they start moving with the same velocity, resulting in distributed capacitance and inductance progressively charging to the full voltage and current. So what happens at the end? So finally, in the infinite transmission line, the wires are infinite long, so the distributed capacitance will never get fully charged to the source voltage, and also the distributed inductance will never allow unlimited charging current. Also, in other words, I can say simply, guys, this pair of wires will draw current from the source so long as the switch is closed and behaving as a constant load. So now look at the characteristic impedance. So what's our main objective? What I said starting of this session. So that is regarding the characteristic impedance and propagation speed. So for the two parallel wire lines with the air insulation as a medium, the characteristic impedance can be calculated as Z0 equals to 276 by root K log of D by R. That means D is the distance between the two conducting wires, and K is, we know, that is the insulating relative permittivity of insulation between conducting wires. Here not is K means here the not reflection coefficient, guys. It is the relative permittivity of insulation between conducting wires, and R is the radius of this conducting material. This is the conducting wire, and this radius is the conducting radius. And similarly for the coaxial, suppose I said no, the transmission line, it may be coaxial cable or two-way, it may be anything. Suppose it is coaxial cable, means we can find out like this. That is Z0 equals to 138 by root K log d1 by d2, where d1 d2 are the inside inner and outer diameters, as coaxial cable contains inner and outer. So that's it, guys. So our main agenda objective is what is we now to find the characteristic impedance. So we have find out the characteristic impedance, and the second one is propagation speed, that is the velocity of propagation. I said no, whenever there is a to and fro whenever there is a transfer motion occurs due to these electric charges, they move to and fro motion, and they travels at the speed of the velocity of light, this charge carriers. So that generates the velocity of the wave propagation. We can calculate by using the formula v equal to c by root k, where k is we know, and the c is the velocity of the light, right? Where k is the, as I said earlier, it is a relative permittivity of insulation between connecting wires, guys. So that's it, guys. Thank you all for watching this.